Okay, now we will continue and prove the equivalence of weak and strong forms. So we have begin from we derive the weak form beginning from the strong form, and in the forthcoming lessons we will see how the weak form will work. So remember that this is our expression, right? In the main body. So as you see, this is our weak form, which has the boundary conditions, body forces, or some source terms, let's say, and then the integral which covers the domain. Now, just take this expression, this term, and apply integration by parts for the proof of equivalence of the weak form. So we apply integration by parts, and then we arrive at this expression. As you see, we have the boundary terms here, and integral which covers the domain. This is okay, and of course from here I can easily say that so this term is equal to B. Remember our strong form, or we can play with it in a different way. We can take this to the left hand side and we can take this term to the right hand side, and then it will form B. So it has to be equal to W multiplied by B plus the boundary terms, since WL is equal to 0. So we arrive at this expression. If we do these operations, simple, we have this boundary term on the left hand side. On the right hand side, we have WAE du dx. At x equal to 0, it is minus. We can take this also to the left hand side of the expression, then it will become positive. Certainly we arrive at this expression. Now here the point is this: remember the condition on the weight function. So the weight function is arbitrary, it's W, and at the Dirichlet boundary condition, at the essential boundary condition, where the displacement is specified, it is 0. We choose it so. Okay. Now, since W is arbitrary, I can choose the W as such a function. And then I will substitute it into the into my expression here. Then I will arrive at this equation. Now here, phi is any function again, but the point with the phi is I choose it positive because it is arbitrary and I can choose that it's positive. Now, of course, the expression in brackets is also positive. And for this integral to be 0, the only way is that this expression has to be equal to 0 within this interval. This is the only way. Certainly, this enforces another thing. This term, which is here, has to be equal to 0. Remember that when x is equal to 0, w is non-zero, and area A is also non-zero, which means that this expression has to be equal to 0. From here, I can easily say that the stress is equal to negative of the traction at x is equal to 0. Okay, so this is basically the proof of the equivalence between the weak form and the strong form. So this is how I write it. That's okay. Now, there is another way. Of course, this is not the only way. Let's continue to analyze the problem. Now, certainly in the domain, I have my expression for the strong form, right? So U is the solution generally. But let's say that U is a function at the moment. So I can say that this is equal to R. And it is valid between from 0 to L. Here, R is called the residue. Okay, it's the residue. At the boundary, at the traction boundary, again, I can define a residue, R0, which is A0 sigma 0 plus T. This is what I define. Certainly, what we imply by the weak form is weight multiplied by the residue plus weight at 0 multiplied by the residue at 0 has to be equal to 0. It's okay. Now let's choose an arbitrary residue and let's assume that the residue is smooth function like this. It can be something like this also. Here it is the C0 continuous, and when it is when there exists a discontinuity, this is C minus 1. Then, of course, since W can be any function, I choose another W. Therefore, I arrive at this expression. If I multiply this function with this one, I will arrive at this function. Now, basically, what weak form tells me is this has to be equal to 0. But as you see, it is non-zero. Now, the only way that this is 0 is since W is arbitrary, Rx has to be 0 for any point between 0 to L. It is the same when it is C minus 1. Here you have a discontinuous solution. Okay, so there is a sudden jump and negative value and the positive value in the vicinity of A. Now this is my weight function. I can choose an arbitrary weight function. In fact, this will result in non-zero value of the weight multiplied by the residue. So this one. It is the same for the boundary. As you see, W0 can be arbitrary. Therefore, I can say that W0 can be 1, for example. So in order this expression to be 0, R0 has to be 0. This basically means that the only way that this expression is 0 is this is 0 and this is 0. This basically shows us that the weak form is equivalent to the strong form.